Okay. Like I brought in notes for both my classes. What don't see that other stuff. Okay. This is last week. Spent the whole week talking about sequences. This whole week is about at least the introductory part of series. We're going to be spending actually several weeks on series. So this week we're just going to get an introduction to them, learn about a couple of basic types of them, and then we'll look at how to tell if a series converges. That's next week, and we'll go from there. But I don't have a whole lot here, so I'm hoping that there'll be some time at the end for any homework questions. Okay.
Well, homework is due on Wednesday.
Okay. Yes, Wednesday. And it's always at 11:59 p.m. So you always certainly have, if you have questions during.
So get started on at 11:30.
So maybe start getting on it, Kevin, tonight and then for tomorrow, and then have questions for Tuesday or Wednesday.
That'll work too. Yeah, that's for early birds to have questions. All right, so. Okay, what do I mean by a series? So the short definition in English is it's just a sum of the terms of a sequence. So we needed to know what a sequence is to even say what a series is. Okay. Sum of a sequence. Okay, so but the thing is, I guess because we're covering one then the other, sometimes students get sequences and series mixed up, and we definitely can't have that. So you side by side. So a sequence, you have some generic terms, A1, A2, A3, and so forth. I'll give an example. Let's suppose that AN is 1 over n squared. So in terms of my sequence would be 1, 1, 4, 1, 9, and so on. Okay. Now, suppose I want to define a series by taking some of the terms of the sequence. So the corresponding series would be written this way using the Greek letter uppercase sigma. And down below, you have the starting index, which will almost always be either 0 or 1. And then we're in infinite series. So if you up top, you would have a stopping index, or if you're never stopping. I'm thinking of an Andy Samberg movie with Rockstar or something, Pop Star, never stopping.
Not stopping.
Yeah, you're going to infinity, and then what it is that you're summing up goes right here. So in this case, AN. All right. Now it could also be written this way: A1 plus A2 plus A3 ... Since we all understand what that means. So to go with this example, I have a sum from 1 to infinity of 1 over n squared. That would be 1 plus 1, 4 plus 1, 9, and so on. Okay. So sequence, we just have a list of numbers. Series, we're adding them all up, or at least we're attempting to. So the question we're going to try to answer with a lot of series is, what is the sum of all of these? Or is the sum at least a finite number? Sometimes it will be, sometimes it won't. We may be, it may be going off to infinity. Okay. So now I need to explain what it means, instead of just talking about a sum possibly going to infinity or converging to a number. What does it mean for a series to actually have a sum? Now, to try to answer that question, I need to define a term called a partial sum. Because it's kind of strange to add infinitely many numbers. But we all know what it means to add a finite collection of numbers. So we're going to use that as our starting point. Okay. So I'm going to define another sequence distinct from the one we're summing. I'm going to call it Sn. Oh, I need to use a different letter here, sorry. Sk. So n is going to start from 1 and go up to k. So in this case, we're not going to infinity. We're summing a finite number of terms. So that's going to be a1 plus a2 up to ak. So you think there's a truncated infinite series because we're cutting it off after a certain point. What that means is the first partial sum will just be the first term, a1. For S2, the second partial sum, we're going to take the previous partial sum, add on the next term. That's going to be a1 plus a2. And then we can keep going. So each partial sum is the one before it plus one additional term. And this can keep going. So what I've done now is to find a new sequence. So the set of all numbers sk that I can get, k going from 1 to infinity, is a new sequence. And it's this sequence that I would use to determine whether the series can be summed or not. I just thrown 2 terms at you, so this being a very important one. Any questions so far just about?
So you have SK in what exactly is the SK brackets in that? What is that?
This is another way of writing a sequence.
Okay.
So it's just a set of all of these numbers for any k going from 1 to infinity. So this is equivalent to S1, S2, S3, and so on, going off to infinity.
S itself is a series, but we're making a sequence out of the series.
S1, S2, S3, that's a sequence. I've not actually given a name to the series. I don't know, but okay. You have a question before I go?
So okay, so just basically saying it's gonna go on to infinity like that, but then partial one is that.
Yeah,
These are partials
yeah, each one of these is a partial sum of the whole series.
of the sequence. Okay.
Yeah. Okay. That's right, because at this point, I have not yet told you what it means, really, for a series to converge. But you do know what it means for a sequence to converge. So now I'm going to use that concept to explain the concept of convergence of a series. So, a series converges if the sequence of partial sums converges. So that's like a formal definition of what it means for a series to converge. We may not necessarily be using this definition directly. We're going to learn various ways to quickly tell if a given series converges, but they're all based on this definition. And then the opposite of that, if the sequence partial sums diverges, series diverges. Now, as an example, you can find a very simple sequence here. AN is just equal to 1. All terms equal to 1. Now, this, going back to what was covered last week, this sequence, does this sequence converge or diverge? It converges because all terms are equal to 1. Then, I define a sum, and from 1 to infinity, a series diverges, because what are you doing? You're adding up 1 infinitely many times. Well, so if you look at the partial sums, S1 would be equal to A1, which is S1. S2 equal to the K partial sum is always going to be equal to K. So SK is equal to K. So as K goes to infinity, well, shocker, K goes to infinity. So the sequence that we're summing may converge, but because the sequence of partial sums of that sequence diverges, the series diverges. So every time I teach this class, I have this heartbreak of someone getting convergence of a sequence or a series mixed up. So trying to bend the butt. Yeah.
Why does when n equals 1 sequence converges?
Okay, because defining this converges, all you're doing is you're taking the limit as n goes to infinity of this. But this doesn't even depend on n. So it certainly has a limit. The limit is 1.
So if it's like, going back to like 1 over n squared,
Yeah.
that would be converges, right? Because it's converging at like 1.4.
This series, I erased it. Yeah, the series 1 over n squared does converge. Now, so one thing about that is, okay, you're adding up all these numbers and 1 over n squared, 1, 4, 1, 9, 1, 16, etc. Those numbers are getting smaller and smaller. So that is at least a necessary condition. If you're going to be adding up infinitely many numbers, those numbers ought to be getting smaller and smaller. And sure enough, that is a way to tell that's one way to rule out a series converging. If you're adding up infinitely many numbers and they're not even going to zero, there's no chance of convergence. If the numbers you're adding up do go to zero, so the sequence converges to zero, like I said, that's necessary, but it's still not enough. You could have a sequence an equals 1 over n. Those numbers are going to zero, but the sum of that series is infinite.
So if you're just saying that a of n, it's just going to one, so it's, okay, so it's just the series. Okay, so a sequence of partial sums, what?
So this is a sequence of partial sums.
That all together or a sequence, or each one of them is a sequence?
This whole thing, I'm describing a sequence, it's a sequence of partial sums. First term, second term, third term. So all the terms of all those partial sums come from this formula.
So it doesn't depend on the function then?
Yeah, it depends on what you're summing.
Okay, so
I'll do another example. Okay. Let an equal 1 through the n. But I can start n at 0 rather than 1. So a0 is 1. So a0, 1 over 2 to the 0, which is 1. A1 is 1/2. A2 equals 1/4, etc. Right. So that sequence certainly converges to 0. But now what about the sum? Right, so
1.70.
all right, so this series right here, this is an example of what's called a geometric series I'll be talking more about later. So the partial sums. So S0 would be just the first term, which is 1. S1 would be the sum of the first 2 terms. So we get 3/2. The next partial sum, we add on 1 over 2 squared, so 1/4. And that's going to be 7/4. And we'll keep going. Now, at this point, you can't really be sure whether this is going to converge to a number. Right, so do one more, this will be 15 over 8. But if you can see a pattern to the elements of this sequence of partial sums, then that can help you determine whether the series is going to converge. So based on these, and if you look at these fractions, 1, 3/2, 7/4, 15/8, what would be a formula that would give these for any value k? And we're getting a fraction. Start with the denominator, that's easier. So what? Yes, 2 to the power k, because we have for 0, 1, 2, 3, we get 1, 2, 4, 8. It's just the powers of 2. Okay. Now look at the numerators.
It's 1.
What?
It's 1.
2k plus 1.
Yeah, I'm sorry, yeah, 2k plus 1.
That's an arithmetic progression. But notice there's the difference between them. One, we add 2, we add 4, we add 8. So an arithmetic progression, like 2k plus 1, you're adding the same amount.
Be It would be K.
2 to the power 2k minus 1,
Warmer. Since I say it again,
2 to the power 2k
uh,
plus 1.
you're so close. Okay, all right. If you look at these numerators. We have one, applied denominator, 1, 3, 7, 15. Now, you see that's a difficulty working with these numbers. Add 1 to each one. 2, 4, 8, 16. Well, how would you express that?
Yeah, K squared?
Not k squared. Like you said k squared, you said 2k, and
Yeah, the same thing as about k.
I think so. I think someone might have said it. Well, we have 2 to the k downstairs, but so it wouldn't be 2 to the k unless I misheard you.
The K plus 1.
Yes, 2 to the k plus 1 gives us these, because 1, 2, 3, 4, and then you subtract 1. We have 1, 3, 7, 15. See where I came from? Let's simplify this. We break it up into 2 fractions. 2 to the k plus 1 divided by 2 to the k is what? This is 2. It's at the base 2. And then minus 1 over 2 to the k. So this is our general formula for a sequence of partial sums. So if this sequence converges, then this series converges. Does this sequence converge as k goes to infinity?
Yeah.
Yeah,
Why? Yes, but why?
so the number gets smaller.
Yeah, this number 1 over 2 to k is getting smaller and smaller. So the sum of this series is 2, the limit of the sequence of partial sums. So this converges to 2 as k goes to infinity. So we can conclude that the sum of this infinite series is 2.
Oh, okay. How do you get the 2K plus 1? That's the.
Okay, because my indices are 0, 1, 2, 3.
Mhm.
Here I have 2, 4, 8, 16, but that's 2 to the first, 2 to the second, third, fourth. So notice the power of 2 that we have here is always 1 greater than the index. That's why it's 2 to the k plus 1. Whereas in the denominators, we had 1, 2, 4, 8. So we had 2 to the k. So, yeah, so these numerators where I've added 1 were always twice the denominator, so it's 1 power of 2 more.
Okay. Hold on a second. One.
Right, so
Okay.
it's trying to express these numbers in terms of k, the index.
Okay.
And here the values of k I've written that correspond to these. So you want a formula where you plug in k equals 0, you get 2, k equals 1, you get 4, and so on. But since these are 2 to the 1, 2, 3, 4, but our indices are 0, 1, 2, 3, that's why you have to add 1.
Okay.
It helps if you look at the 15 over 8, if you add 1 8, you get 16 over 8, and that equals 2. So that's where you get your first number from. So how do you get the 1 8 out of that? And that's where you're getting the rest of the equation.
Yep. Now we see that the sum of this series is 2. I can tell you what is the first, but may not necessarily be the last. Calculus 3 bar joke. Infinitely many mathematicians walk into a bar, and the first one orders a beer. The second one orders half a beer. The third one, fourth of a beer, eighth of a beer, and so on. So the bartender gets fed up with this, just puts 2 beers on the counter and tells them you gotta know your limits. I know. Not the last time I'll make you wrong. Okay. Okay. Oh, interesting. I have this whole example written out in my notes and I had forgotten how to put it there and I just went ahead and did it. So, okay, that's convenient. Okay. Okay, before I continue with, working on series, including geometric series like this one, I'll take a moment to explain, why series are important. Later on, after we work with series such as these and figuring out whether or not they converge, we're gonna see, power series. Power series are series that describe a function of x, rather than just a number. For example, if I describe a series 1 plus x plus 1/2 x squared and so on, that is a series that would describe the exponential function e to the x. Sine x and cosine of x can be described using within series. And that's important because it's a way to approximate functions like sine or cosine or exponential using very simple functions to work with, like polynomials. In fact, it's through the use of series that functions like those are evaluated by your calculator or your computer. Because computers only know how to add, subtract, multiply, and divide. It has no mechanism for evaluating a function such as like a transcendental function or trigonometric function. It has to use some algorithm that involves only those 4 basic operations. And series are how that's accomplished. Actually, when I was in high school, I first learned about trigonometric functions. And the way we would evaluate them is go to a table in the back of a book where we had entries after entries of values of sine or cosine, and use the entries in the table to get the value. Now, this was 1984, so we may have ways of defining these functions exactly, but we don't have any way of practically computing them. Not exactly, only in certain special cases, like cosine of 0 is equal to 1, or e to the 0 is equal to 1. Otherwise, an approximation is necessary, and series are very helpful for that. Now, power series are still a couple weeks away, and it's probably going to be the hardest part of the class, so brace yourselves. Oh boy. But by then we'll have seen series for a while, and hopefully it won't be so bad.
When does that begin?
We'll see. So next week I do first test. So I guess about 2 weeks. That'll be the last stuff before the midterm, but I'll give you plenty of help to prepare for the midterm. And after that, the class gets easier, so have to hang on. Okay. The easiest kind of series to work with is a geometric series. The second homework will mostly be problems about this kind of series. And the example I just did is actually a geometric series. So any series of this form, infinity, some number a times some other number r raised to the nth power. In some cases, a series might not be written as starting at n equals 0, but if it isn't, it's a good idea to write it that way. And I can show you how to do that because it'd be easier to work with. So the number a and the number r had to be specified. So in this example, r was equal to 1/2. We're going to keep multiplying by to get from one term to the next. and A in this example, which is equal to 1. So in general, A is always the first term, because this series is A plus AR squared, AR cubed, and so on. So if you were to write out the first few terms, whatever first term is, that's A. And then notice to get from one term to the next, you're always multiplying by R.
Okay.
So R is a ratio of terms. And for most of our time seeing series, you'll be tasked with figuring out, does the series converge or not? In many cases, even if you know it converges, you won't know what the sum is equal to. But you're not being asked for that. You just asked, does it converge or diverge? This is an exception. For geometric series, you can figure out, does it converge or diverge, and figure out what the sum is if it does converge. Okay. So there actually is a formula for the sum of a geometric series, and I'm going to derive it for you now. What is a geometric series if it has a sum? So to show you, I'm going to resort to trickery. I'd like to find a partial sum, Sn, be equal to I'll write it this way. A plus AR squared, all the way up to AR to the n. So I'm stopping at a particular index n. Okay. Now, suppose I take both sides of this equation and multiply them by R. So R times Sn. So I'm multiplying all of these by R. So I have AR squared, AR cubed for multiplying these by R, and so on, all the way to AR to the n plus AR to the n plus 1. So it turns out that by multiplying by R, I get mostly the same numbers. AR in both, AR squared in both, everything up to AR to the n in both. With the exception of the very first number here, A, it's only the first one, and then AR to the n plus 1 is only in this one. So I'm going to subtract these two equations. Then I get Sn minus Rsn on the left side. On the right side, most items cancel. What remains? The A what?
A plus AR to the plus 1.
Yes, with what sign? Minus. Yeah, because it's down here. Okay. All right, so now I can do a little factoring here. On the left side, I can factor out Sn, the nth partial sum. I should label this. And on the right side, I can factor out A. So now I have a formula. So assuming R is not equal to 1, Sn is equal to A times 1 minus R to the n plus 1 over 1 minus R. So this is a formula that actually it's come in handy a number of occasions, even outside of Cal 3. If you have any kind of sequence like this where you're stopping at a certain point, you have this form that expresses this sum of all these numbers in closed form, so without having to write out a whole bunch of terms.
So you're taking Sn out of that, and you're also taking the A out. Okay.
Yeah, it's factoring out whatever I can. So now we need to see, so this describes the sequence of partial sums. Yes.
Let's say F R does not equal 1.
If R is not equal to 1. Yes, otherwise it'd be divided by 0. Actually, I can fill that in. If R does equal 1, I'm just adding up A a whole bunch of times. So then it gets A times n plus 1. Now, we need to see what happens to this expression as n goes to infinity. Now, the only part of this that even depends on n is this right here, the R to the n plus 1. So what is going to happen to this as n goes to infinity?
The R is gonna get exponentially larger.
Depends on it.
So it's going, so,
Yes, it depends on the value of R. So for example, if I set R equal to, let's say, 2. Yes, the 2 to the n plus 1, that's going to go up to infinity. Whereas if I set R equal to, let's say, 1/2.
it's gonna be, yeah.
Yeah. So what we can say is that the limit as n goes to infinity of Sn, which is also the sum of a whole series, is equal to, so if R is strictly less than 1 in magnitude, this part here will go to 0, and then we just have what's left. A over 1 minus R if absolute value of R is less than 1. So this right here describes the sum of a geometric series, if it has a sum. So if absolute value of R is greater than or equal to 1, it diverges. So now we know under what circumstances a geometric series converges, and if it does converge, we have a formula for the sum, A over 1 minus R. Like an example I did before this, where A was 1 and R was 1/2. Then you plug those two in and you get 2, which is what we arrived at a different way. A lot of the homework problems for this section, so homework 2, are really just using this. Figuring out what the value of A is, what the value of R is, using the value of R to determine if it converges, and if it does, just using this formula to get the sum. That's most of what it's asking for. All assignment long. It'll get pretty monotonous. Any questions about how that formula was arrived at? I have. Actually, all I have left are some examples of geometric series. Okay. First example, I'll have infinity e to the n over 10 to the n minus 1. Now, notice here I'm starting from n equals 1, whereas this whole time I'm running a geometric series and starting n equals 0.
Right, so the other one, so if absolute value of R is greater than or equal to 1, then it doesn't, there's no limit.
Right, yeah, this formula does not apply.
Top number keeps growing, so.
Yeah.
It's approaching infinity.
Never just no limit, okay.
What's this formula that you wrote?
Oh, e to the n over 10 to the, Yeah. 10 to the n minus 1. So this, I started at n equals 1. So you need to be careful about getting the values of a and r, because you want to use this formula if you determine that the series converges. And that's where you use what I mentioned earlier. A is always the first term. R is a ratio of terms, like A2 over A, second term over first term, third term over second term, and so on. So if I were to write out what the terms would be, so for n equals 1, I'd have e to the first, which is this e, over 10 to the 0, which is 1. So this right here, A. And then if I look at the next terms, I'd have for n equals 2, I'd have e squared over first cubed over 10 squared, and so on. So whatever you're multiplying by to get from one term to the next, that's your R. So A turns out to be equal to E in this example. And what is R? Sorry,
1 over 10.
Yeah, E over 10. Okay. So once you have the values of A and R, however you got them, you check, is this less than 1 in absolute value? Does anyone know any decimal digits of E off the top of your head?
Eight.
Yeah, it's 2.718281828. 5%. But yeah, less than 10. That's what really matters here. So that's why our less than 1, it converges. Now you can use the formula for A over 1 minus R. So we have E over 1 minus E over 10. And then you can simplify that if you like. So for example, if you multiply top and bottom by 10, with 10E over 10 minus E, and that's the sum. So first term, ratio of terms, check R, is it less than 1 in magnitude? Formula, done. So that's most of the second homework, wash, rinse, repeat. What about this one? If you have a series like this, you prefer it as starting at n equals 0, but it's written this way, starting at n equal 1. There's a way to transform the description of a series, start at a different index. And it wasn't really necessary for this example because we could figure out the sum this way. But it's a good thing to know in general. Performing was referred to as an index shift. of a series. So with a series we're starting with, I'll just repeat it. I'd like to write this as a sum of starting from n equals 0 of something. But what is the something? So if you are decreasing the starting index, in this case, I'm decreasing the starting index by 1. Then to compensate for that, in here, wherever you see n, you replace it with n plus 1. So e to the n plus 1 over 10 to the n. So that's how you perform an index shift. Whatever amount you're decreasing your starting index by, you are increasing n, the expression inside. So these actions compensate for each other so that the expression you have is equivalent to the original one. A class I taught last semester, Math 415, we were doing it. For observations a lot, index shifts all the time. So it's one of those good to know skills. I can do every single example in the notes because I wanted to allow some time for homework questions. Or if you don't have any, we'll do those last examples. But this next example is particularly important because I can guarantee you there's going to be a midterm problem just like this. That's what I want to get everybody paying attention to.
Okay, so that's en over 10 over 10 and what?
But
Here, yeah.
here, e to the n over 10 to the n minus 1. One application of geometric series is if you have a repeating decimal and you want to know what fraction that repeating decimal is equivalent to, a geometric series can help you figure it out. So suppose I have this repeating decimal, 1, 4, 2, 8, 5, 7 repeating. So that could be written as 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, so on. So the question is, this is equal to what fraction? Some of you may know off the top of your head, but the point is, we're going to have a systematic way of getting it for a repeating decimal you might not recognize. So the idea is to write this number as a geometric series by examining each repetition of a sequence of decimal digits. So this number right here, if we forget about the rest, this number right here is equal to 142,857, the digits themselves, divided by 10 to the 6th of a number of digits you have is what goes here. So this exponent is the number of digits that are repeating. So that is a number described by this decimal here, 0.142857, not repeating. Now, to capture repetition, we add on more terms. So this number right here would be the same as this one, except you're shifting 6 more decimal places smaller. This would be 142,857 over 10 to the 12th. What number would describe the next block of repeating digits? Yes, 142,857 over 10 to the 18th, and so on. So now you can use this description of the number to figure out what geometric series you're dealing with. What is A, what is R? So this is a sum, A, R to the N, where A is going to be the first term. It's going to be the sequence of digits that you have, divided by 10
Inputs.
to that many digits. And then what is the R? What do I multiply by to go from one of these to the next?
1/10^6.
Yeah, 1/10 to the 6. Okay. Well, it definitely converges. R, however many digits you have, no matter how few, you're always going to have at least one. So R is always going to be a positive number less than 1. So we know it converges. So what is a fraction? It's going to be, we use the formula A over 1 minus R. And let's see what that turns out to be in this case. So I fill in the value of A. And then I'm dividing by 1 minus R. That's 1 minus 1/10 to the 6. But now I'm going to simplify. So I'm going to take this 10 to the 6 and distribute it through this expression in parentheses, and that's going to give me 10 to the 6 minus 1. So we get 142,857 over 9999999, which happens to reduce to exactly 1/7. But this is the key right here. What it always works out to be, so shortcut for a test, hint, hint. It's the digits that are repeating divided by that many 9s. Always. Now, can it be, is now after that, you check whether that's in lowest terms. In this case, it wasn't. It just depends on what the numbers are. So another example. 0.181818, so on. So that would be 18 over 99. This is definitely not in lowest terms because the numerator and denominator are both divisible by 9. Turns out to be 2 over 11. Okay. I'll do one more that's a little more complicated because it's not entirely repeating. 0.083 repeating. So what you would do is you would break this down into 2 parts. So 0.08 that stands on its own, and then you have 0.3 repeating divided by divided by 100. So when you figure out, so we have 0.08, and then the 0.3 repeating, for that you could use the method I've described. It's 3 over 9. But that's just 1/3, of course. So okay. 0.08, that is the same as 8 over 100. And on the denominator and all that, you get 25 over 300, which is 112. Okay, that took a bit, but you get the idea that if you have a decimal, that is not entirely repeating, you can focus on the part that is repeating. And then work it into the rest, actually figure out what fraction is equivalent to. I'm not gonna do this on the test. The question about repeating decimals. There are 15 minutes left, so if you have a choice. I do have more examples, or if anyone has homework questions, this is a good time to ask it. Or let's do a whole 2 days of now, so. And I know some have already done it. Not very many though. Okay, that. When you do see this problem on the test, I'll be fine if you're jumping straight to this step. Because you're gonna be freaked out about the other problems. Consider that a gimme. But I know someone here is gonna forget. It always happens. But hope springs eternal. Okay. Another example. Minus 2n, 3 to the n. So anytime you have a series where you can express it as some constant factor times something that's raised to the nth power, that's a geometric series. May be helpful to write it differently. Or easily see what is A, what is R. So since everything here is raised to the nth power, I can write it this way using the laws of exponents. 2 to the minus 2 times 3, all raised to the nth power. So this right here, this number inside, that's R. So this is sum AR to the n, where A is what and R is what? A is 4. Yeah, so 2 to the minus 2, that's 1/4. So it converges. So now I can just apply the formula, 1 over 1 minus 3/4.
One second, can you leave can you leave the bottom one?
Sorry, what?
Can you leave the bottom one?
Oh, this, okay. Oh, okay. I actually grew up in Massachusetts, so I'm as Yankee as one could possibly be. And I guess between Massachusetts and Mississippi, people in both places probably think Gary talks funny. So one of my math teachers would have pronounced this as FOA.
In Massachusetts?
Yes. Well, I got very lucky in that well, I grew up not far from Boston. My parents were not from there, so I did not pick up a Boston accent. I couldn't have dealt with that. But-
It would have been your choice.
Hmm. Okay. Any questions about this one? Or that one since it's still on. Okay. Right. You can take this next example as like a preview of things to come. We mentioned power series. So here we have x minus 2 to the nth power over 2 to the n. So this can be described as a geometric series. It's just that the r is not just a fixed constant. It's a function of x. So this number here is the r, x minus 2 all over 2. So whether this series converges or not depends on the value of x. So what you would require converges if and only if absolute value of x minus 2 all over 2 is less than 1. So that would mean that so x minus 2 absolute value must be less than 2. So that means that x has to be between 0 and 4 for this series to converge. So if x does fall into this range, anyone tell me what the series would converge to using the same formulas in every example?
Why was a 1 in this case?
The first term, if I plug in n equals 0, this whole thing's going to give you 1.
We want.
More or less.
Oh, we're back here now. Okay.
Over there.
Okay. Oh, you're saying it's 1 over x? Okay, let's find out. So it's a over 1 minus r still applies. So it's 1 over 1 minus r, which is x minus 2 over 2. So we multiply top and bottom by 2 because we have too many denominators in this fraction. Fractions are annoying enough as it is. Okay. Okay, so it's equal to 2 over 4 minus x. Was there a mistake or something, or?
No, I did it on surface.
Oh, okay, yeah. My professor said, and I quote, "What may be obvious to me is often wrong." So, and sometimes what I write here is going to be wrong. So, so just as I had to check all your work, be sure to check mine too. Okay, but any questions about how this was arrived at? I was interested about this example. X has to be between 0 and 4. Well, okay. Sometimes we actually be more careful about this. I have to change this if and only if to an if. If this is true, the series definitely will converge. Now, it definitely diverges if the absolute value of x minus 2 all over 2 is strictly greater than 1. So that we know for sure. If absolute value of x minus 2 all over 2 is equal to 1, It may or may not converge, it just depends. So if you look at this formula here, if I plug in x equals 4, it's undefined, it's going off to infinity. Whereas if I plug in x equals 0, at least this is well defined. And using things I'll show you later, if I were to plug in x equals 0 right here, yes, it actually does converge. So what happens is middle ground between this situation and this one. When it's a power series, it's murky. Okay. 5 minutes. Okay. Oh. I have the same example in here twice. That's the geometric series I was just showing you. But the first example about, r equals 1/2. So. All right. So actually, development further. There's on Wednesday, we're going to see another kind of series called a telescoping series. But in that case, also we can figure out if it converges, what the sum would be. So that's going to be the kind of series we're doing on the second homework. So those of you who haven't finished the first homework, Wednesday would be an excellent time for you to get any questions answered. Okay, I guess that's it. Yes, go ahead and back up.